In this video, we're going to, again, do confidence intervals. But we're going to not make any assumption that we know the standard deviation of the population. The biggest thing that we're going to lose is we're going to lose our nice, consistent critical values. We can't use the z's anymore. And what we're going to use instead is going to come from beer. All right, so Chief-Aru has been patiently coming along, but she knows that to know the population standard deviation, we have to know the population mean to begin with. And if we know the population mean, why are we trying to estimate it using the samples? So Chief-Aru wants to know, how can we estimate our population mean without making this really dumb assumption? And it turns out that you can still do this, thanks to Guinness, or in particular, someone who works there. And I'm not actually kidding about this. This comes from the brewery, okay? All right, so since we usually only know the sample standard deviation, right? Remember, that's S. We don't actually have access to the standard normal distribution approximation, okay? So what do we do instead, right? Since we can't use the standard normal distribution, it turns out there is another distribution that actually does do the right things. And we call this distribution, right, this distribution using our sample standard deviations, the student's t-distribution. And it's in your book, okay? So our student's t-distribution is slightly different from the standard normal distribution. And the critical values that come from it these are going to be called T alpha of 2's. They're going to be dependent on the size of the sample. So the shape of the distribution changes slightly based on how big our sample size is. Right? For a generic standard normal distribution, it doesn't. Okay? The width of the peak does, but the shape itself does not. Now, this fact was discovered in 1908 by William Seeley Gossett. So he was a statistician that was working for Guinness Brewing Company. And they actually forbade him from publishing it because they thought it was a corporate secret. And so he published it anyway, but he published it under the pseudonym Student. And that's why it has this name today. All right, so one of the things that we really need to do to get access to these critical values is to define something called the degrees of freedom of our sample. Right? For a sample size n, there are n minus 1 degrees of freedom. Right? So if we have 50 data points, we have 49 degrees of freedom. If we have 112 data points, we have 111 degrees of freedom. And it shouldn't be surprising that n minus 1 crept in here, because if we remember when we calculated our sample standard deviation, this n minus 1 popped in. So it's just popping back at us in this case. All right, a quick example. If we have a sample standard size 38, there are n minus 1, so 37 degrees of freedom. If you look at the table, a 95% confidence level with 37 degrees of freedom coming out of the table comes out to be 2.062. Okay, so in reference, our critical z-value for 95% confidence was 1.960. Okay, so this is larger. In general, our critical t-values are always going to be larger. In fact, our student's t-distribution actually begins to look really approximately normal as the sample size gets arbitrarily large, right? In the limit to infinity, they actually are equal. But for a finite n, the the student's t-distribution is a little more spread out, and our critical values are going to be larger. All right, so we do this thing by calculating a margin of error, right? If we only have our sample mean x bar, we can't expect it to be the population mu, so we calculate a margin of error, which we're going to call m, and we look that far on either side of x bar, so mu is going to be within some confidence level between x minus m, x bar plus m. Again, the margin of error is going to depend on several things. How confident we want to be that our population mean is in the interval. This is going to be carried by our critical value t alpha over 2, and that's going to depend on our degrees of freedom, which is dependent on our sample size. It's going to be dependent on the standard deviation of our sample, our S. Okay? We don't have access to the standard deviation of the population, so we use the next best thing, our standard deviation of the sample, and it's also going to depend upon the sample size, and it's going to depend on it two different ways. Okay? There's going to be a 1 over square root of n that's going to pop in here, but it's also going to affect our critical value through the degrees of freedom. The calculation for our margin of error is going to be our critical value times our sample standard deviation divided by the square root of n. The form of this equation is going to look similar to what we did for the first time we looked at margin of error. The only thing that's different is what our critical value is and where our standard deviation comes from. The t alpha over 2 is called our critical value, and it's going to depend on our confidence level, right? 90%, 95%, 99%, etc., as well as our degrees of freedom. But in general, as our confidence level goes up, it gets bigger. The critical value t alpha over 2 is also going to go up, and our margin of error is also going to increase. S is our sample standard deviation. As our standard deviation increases, the margin of error increases, and so our confidence interval will also increase. N is our sample size. As our sample size increases, the margin of error is going to decrease. Okay? Our critical value is also going to decrease. So that's something to also look for. So that's a little different. And once we have our margin of error, we calculate our confidence interval. X bar minus our margin of error to x bar plus the margin of error. And we say we are whatever percent confident that the true mean, mu, is between x bar minus m and x bar plus m. And as always, in reality, if we take sample size n over and over, whatever our confidence level percent of those confidence intervals will contain the true population mean. So next, let's do some calculations.